We will have a review for midterm number 1. This midterm is for EEMG 389, Fundamentals of Electric Machinery, now in spring 2015. I am Professor Simons, and I will start now my topics for midterm number 1. Those are the topics you should be ready by this time. You should know by this time. Circuits basics, single phase power, 3-phase systems, 3-phase power, magnetic circuits, magnetic materials, magnetic fields, ideal transformer, real transformer, the transformer equivalent circuit, transformer tests, PU system, per unit system, and transformer performance. You should expect in this midterm number 1 3 questions. So from all those topics, you'll be tested on magnetic circuits, real transformer, the transformer equivalent circuit, PU system, transformer performance. And transformer performance is related to the transformer tests. In this midterm, you have 50 minutes. You should time your progress, and you should expend 20 minutes on question number 1, 20 minutes on question number 2, 10 minutes on question number 3. Each question has sub-items. Those sub-items will equally contribute towards your grade. So for questions number 1 and number 2, you have sub-items A, B, C, and D. For question number 3, you have the sub-items A and B. So you should pay attention with your time, and you should allow 5 minutes maximum for each sub-item. Of course, if you work faster in one sub-item, you have that time available for next, but just time yourself in order to be possible to work in all those sub-items in your 50 minutes. So for this review, I could never cover all the problems related to this section for exam. This would be very exhausting, tiring, and boring. But I selected 3 problems which I believe they represent questions that I plan to ask you for midterm number 1. Please take this opportunity in preparing for this exam and this break in our lectures, so you can devote yourself to learn, mature yourself in the topics that you have been working so far, and learn outside the box. For your preparation for this midterm, you should read the book chapters in advance so you understand further details and you enhance your learning. You should review the handouts I gave you in class. You should study and prepare the homework problems, all the homework problems. You should practice all the problems that I gave you in class. Do not forget, you have to bring your calculator. Of course, you have to know how to use complex numbers, and you have to understand how to perform Cartesian to polar conversions, understand very well how phasor analysis of sinusoidal sources are solved, and you should be able to understand and draw phasor diagrams. So for your first problem I want to work is a problem that I selected from homework set number 1. So this problem is, you solve that in your homework set number 1. It's the problem 1.5. The magnetic circuit of figure P1.5 provides flux in the two air gaps. The coils with N1 700 turns and N2 200 turns are connected in series and they carry a current of 0.5 amp. Neglect leakage flux, reluctance of the iron, that means you are assuming infinite permeability, and neglect fringing at the air gaps. You have to define, you have to calculate the flux and flux density and the air gaps. So you see a figure here, and if you go to the next page, you see that we have on your left the magnetic circuit showing all the core dimensions, the lengths, the air gap length, the depth of the core. So we also see the two terms, N1 and N2. Pay attention that N2 is wound opposed to N1. So if you have a current flowing in series like the indication, you have flux opposing to each other. On your right, you see the magnetic equivalent circuit. You have a current source. The current source, this is an equivalent electrical circuit. So the current source represents the Ni. So N1 minus N2 multiplied by I. Why there's a subtraction? Because the coils are opposing to each other. Then you have the reluctance to the left, reluctance to the right. You see here that we are calculating Rg1 and Rg2, which are the reluctance that happen because of the air gap on the left and on the right. Your core, you assume the permeability to be infinite, so you just have to consider the air gap reluctance. Now on the next slide you see that we are calculating the reluctance. Initially we have to assume here the areas for the air gap because we are not considering any fringing effect. So the air gap area on the left and on the right, they are the same. So you see here it's 6.25, 10 into minus 4 square meters. You can calculate the reluctance for the air gap Rg1 and Rg2. You take in consideration the length. 4 pi 10 minus 7 is the air permeability, and the air is the same, 625 10 into minus 4. So the reluctance for the air gap 1 is 0.637 10 into 6 ampere turns per Weber, and Rg2 is equal to 1.275 10 into 6 ampere turns per Weber. So in the next slide we are calculating the flux for each loop. So the flux 1 and the flux 2, they are the total Ni N1 minus N2 multiplied by I divided by the respective reluctance. So Phi1 is 0.392 10 into minus 3 Webers. Phi2 is 0.196 10 into minus 3 Webers. So what's missing now? To finish this exercise, you should compute from your flux in the air gap Phi1 and Phi2. You should compute the flux density. So here you see the total flux in both air gaps is 0.588 10 into minus 3. And if you want to compute the flux density B1 and B2, they are related by flux divided by the respective area. Okay, the respective area is considered to be the same because you don't have any fringing. Phi1 and Phi2, they are different. They were calculated before. So B1 is 0.627 Webers per square meter or Tesla. Okay, and B2 is 0.3135 Webers per square meter. I am suggesting an extra problem for your own understanding, so you should work yourself on these 3 bullets. If you assume only the winding with N1 turns, what's the inductance for that winding by itself? So it's the self-inductance for the winding 1. Then you look to the inductance for the winding with N2 turns. What is the inductance for that winding with N2 turns? That means the self-inductance. Now, if you connect them, so the third bullet is what is the inductance for the total winding? And in this particular case, you have to remember that one coil is opposing the flux of the other for the series connection. I didn't add another bullet, but you could also think what happens when you add 2 inductance in series and they are not opposing to each other, but they are helping the flux on the same direction. Remember to use your right hand and your thumb. Your thumb goes towards the current, you curl your hand, and you see the direction of the flux. So you know which flux is opposing to each other or it's helping to each other. Our second problem is a transformer problem that I used in the class. So the second problem is not from your homework, but it was a problem developed in our lecture in order to teach models, and I'm bringing here also the PU system. So this problem can be stated like this. A single phase transformer is rated at 25 kVA. The high voltage side is 2500 volts. There's a turn ratio 100 to 1000. This transformer was tested in open circuit with the high voltage side open, with measurements of 100 volts, 6 amps, 400 watts. While in short circuit, the measurements were 50 volts, 100 amps, and 1800 watts. So a few reminders here. When we are measuring, usually we are measuring with instruments that will give you the RMS value. So 100 volts, 6 amps is RMS, 50 volts and 100 amps is RMS. Also, the turns ratio 100 to 1000. Don't worry much about this. Sometimes the turns ratio is given in the rated voltage, but here could be, okay, what matters is there is a relationship that we could say that N1 is 100, N2 is 1000. And always remember that a transformer is bidirectional. So the definition of primary and secondary are not really important, particularly for these transformers in power systems. We usually say high voltage side or low voltage side. So in this problem you have 4 sub-items. Find the model related to high voltage side. Number 2, find the model related to the low voltage side. Find the model in PU, indicating clearly all the bases. And number 4, suppose the transformer is loaded at 80% of their capacity with a power factor 0.9 at the low voltage side, with rated voltage at the high voltage side. Calculate the efficiency, the internal voltage drop in volts, and the regulation at this particular operating point. So on the next slide, you see that we can start with the open circuit measurements. The dissipated power of 400 watts is taken by the equivalent resistance representing the core loss, RC1. So RC1 would be 100 volts square divided by 425 ohms. So we can calculate IC1. IC1 is the 100 volts applied there, divided by the 25 that you just calculated, 4 amps. So you see in the circuit that 6 amps are coming in through the core loss resistance. We have 4 amps, and we have to calculate the current through the magnetizing inductance LM1. Because this is in RMS, they will have to be added in square. So I1 square RMS is IC1 square plus ILM1. So we have 36 is 16 plus IM1 square. So the magnetizing current is 4.47 because we know the voltage across is 100 volts. We divide by 4.47. We have the value for the reactance there. The magnetizing reactance is 22.37 ohms. So on the next slide, you see that we are considering here the turns ratio. If you want to reflect to the high voltage side, we have to multiply by 10 square. So the magnetizing inductance on the high voltage side is 2237 ohms. Then here we start the short circuit measurements. We are going to use those values because you are applying a low voltage for short circuit. In this case is 50 volts. Even though you have a magnetizing branch in parallel, we neglect. Of course, your model will be an approximation, but it's easier to use it. So considering that we can neglect the power dissipated by RC1, the core loss RC1, so we have this equivalent circuit here, R1 in series with XL1, in series with XL2 prime, in series with R2 prime. So we can easily find the Req, which is the sum of R1 and R2 prime, and that is 1,800 watts divided by 100, so it's 0.18 ohms. The equivalent total impedance should be the 50 volts applied divided by 100, 0.5 ohms. And the equivalent reactance could be calculated by considering that the magnitude of the impedance square is equal to the real part square plus the imaginary part square, R equivalent square plus X equivalent square. So we can find X equivalent, which is the sum of XL1 and XL2 prime. That's 0.4665 ohms. We are using primes, XL2 prime and R2 prime, because we are reflecting the one side to the other side, okay? We are reflecting to the high voltage side. So the next slide shows you the model referred to the high voltage side. We have the high side here on the left, a parallel branch here of the core losses, 2,500 ohms, the magnetizing reactance, J2237 ohms. We have the lump, the merge of the resistance, R1 and R2 prime, 0.18 ohms, and the merge of the leakage reactance, J.4665 ohms. So on the right side, we consider that we have V2 prime. We have to remember that there is an ideal transformer connect to that. So the ideal transformer does not have any parameter, any passive component. It's only a voltage ratio, a current ratio, and of course an ideal transformer will maintain the apparent power from one side to the other side, okay? So you see here that on the next slide that we have 1,000 to 100 transformer. The impedance should be referred by multiplying or divided by 100, because it's 10 into square, okay? So the ideal transformer could be connected like this diagram shows on the left. It could be omitted as long as you know exactly what model you are using. So the model related to the low voltage side is represented here. We have an ideal transformer on the left. Then on the right side of the transformer, we have the magnetizing branch, RC double prime, XLM double prime, and then we are also bringing the series resistance and the series leakage, REQ double prime, XEQ double prime. So by using a factor of 100, we divide by 100. So REQ double prime is 0.0018, XLQ double prime is 0.004665, RC double prime is 0.25, XLM double prime is 22.37 ohms. So on the low voltage side, we have smaller impedance that are reflected from the high voltage side by the turns ratio square. So continuing here, we want to discuss the PU model. So the model in per unit is very simple, as I discussed in class. We do not use the magnetizing branch, okay? We just assume that we have V1 in PU on the left, V2 in PU on the right, and the equivalent impedance in PU as a series connection from one to the next. So this is the core system model used for flow analysis, for voltage regulation, voltage drop. So this model is simplified, but it's very useful for power transformers. It's very important to show the base. So the apparent power base, S base, is the first one we have to note, 25. On the voltage side as defined, and the transformer is 2500 volts. The voltage on the VB2, the voltage based on the low voltage side is 250 volts. So S base, VB1 for high voltage and VB2 for low voltage, they are considered the rated parameters for the transformer. Now we have to find the equivalent impedance in PU. In order to find equivalent impedance in PU, we have to calculate the base for impedance on the high voltage side and on the low voltage side. So here in this box, we are calculating ZB1 for the high voltage side. It's very interesting to express the voltage square in kV and the power in MVA. Why? Because kV square is giving you a 10 into 6, MVA is also 10 into 6, so we don't have to be concerned about those powers of 10. So take our voltage, express in kilovolts, square it, take our power, express in MVA, that's going to be in your denominator. So you are basically dividing 2.5 square by 0.0025. So the base impedance for the high voltage side is 250 ohms. And the same can be calculated on the low voltage side. Is 0.25 is 250 volts, so it's 0.25 kV, 0.25 square, kV square, divided by the apparent power in MVA, 0.025. So the impedance is, the base impedance is 2.5 ohms. So you can calculate as shown here on the next slide, you can calculate the equivalent impedance, the resistance and reactance in PU. So if you look to the high voltage side, you take 0.18 divided by 250 ohms, it's 0.00072. The X equivalent in PU, if you look to the high voltage side, is 0.4665 divided by 250, so that is 0.0018666 ohms. So the PU equivalent series impedance is 0.00072 ohms plus J 0.001866 ohms. If the transformer is loaded at 80% of their capacity, the apparent power, the rated power, is 25 kVA. So the operating apparent power on this condition would be 25 multiplied by 0.8. So your transformer is converting 20 kVA. The low voltage side will have a power because power factor is 0.8, we take the apparent power, multiply by 0.8, so it's 20 multiplied by 0.8, 16 kilowatts. And the reactive power, you have to remember that S square is P square plus Q square. So Q, which is the reactive power, is square root of 20 square in kVA minus 16 square in kilowatt. So it's 12 kVAR, okay? kVA is for apparent power and VAR is for the voltage ampere reactive. Your efficiency will be calculated by your output power divided by the input power, and we have to remember that your transformer is usually connected in constant input voltage, so the core loss will be considered to be constant because we have a magnetizing branch in parallel with the voltage coming from the feeder, okay? So we can calculate core loss as the voltage on the high voltage side square divided by the core resistance is 2500 square divided by 2500. So the core losses are 2500 watts, and they do not vary with the operating conditions. However, your operating condition, that means how much power you are converting, will give you different copper losses. So the copper losses are variable, and they will depend on the load. For this operating point, the copper losses are the current I1 on the high voltage square multiplied by R equivalent 1 on the high voltage, okay? So we have to find the current on the high voltage side for this operating point. You have to remember that V2 prime is considered to be 2500. So I1 HV will be 20,000 divided by 2,500. It's 8 amps RMS. So your copper losses will be 8 square multiplied by 0.18, 1152 watts. So this transformer actually has very low copper losses and kind of sizable core losses. So that means the core maybe it's not optimized, but the windings have a very thick gauge for the wire. That's the idea here. So the efficiency at this operating point will be 16,000 divided by 16,000 plus 2,500 plus 11.52. The efficiency is 86.43%. Okay, so we have to calculate now the internal voltage drop in volts. We have to look to the voltage drop across the total internal impedance, the equivalent impedance that connects V1 to V2 prime is 0.18 plus J 0.4665. Okay, we know the current there. We calculated on the previous slide. It's 8 amps. So the magnitude of this impedance is square root of the resistance square plus the reactance square, 0.5 ohms. So the voltage drop, that voltage drop is composed of two elements. One is a resistive voltage drop, another is a reactive voltage drop, because you have to remember that we have AC flowing, okay? So there is a voltage drop across the leakage inductance as well. So we just calculate the magnitude of that impedance is 0.5. So 0.5 multiplied by 8 is 4. So 4 volts is the voltage drop, the internal voltage drop. The regulation at this operating point, you have to remember the definition of voltage regulation is your VQ prime magnitude for non-load conditions minus the magnitude of VQ prime loaded divided by the magnitude of VQ prime loaded. We have all those numbers, we have all those magnitudes. VQ non is weighted value 2500. The V2 prime loaded in this particular operating point, we subtract 4 volts, so it's 2500 minus 4. And on the denominator is again 2500 minus 4. So 4 divided by 2496 is 0.16%. That means if you apply a voltage on the high voltage side, if you load your transformer at 80% of their capacity, you only lose 0.16% of the voltage applied on the low voltage, on the high voltage side. So again, that's an indication of your low losses, internal losses in your copper losses. Okay, so this transformer does not give you a lot of loss, I mean a lot of voltage loss, but the efficiency is not very good. So you have to be careful when you discuss loss. Loss could be a power loss in watts, or sometimes the power systems professional we just say loss, meaning as the loss of voltage. So here we have a perfect example that we have a low voltage loss of only 4 volts, and we have a lot of losses in the core, okay, because the efficiency is not very high. So I would suggest an extra problem for your own. It's very important that you understand how to draw phasors, how to evaluate phasor diagrams. So take a look in our book, take a look in my notes, try to understand how the phasor will represent the locus of the operating points of the transformer. And then, for this particular problem, draw a phasor diagram in scale that represents the steady state operation of this transformer at this particular operating point. So my suggestion is to take a graph paper, you know, like that yellow paper with divisions, squares. Then start with your V2 prime, making scale, so use whatever scale you want to draw the magnitude of the voltage. Then you have to find the angles exactly. So if you do things in scale, they become a valuable tool for you to understand how your system behaves. So this is all for problem 2, and I will start now problem 3. The last problem in this review session is from your homework set number 2. So here we have the first slide. The statement for this problem is the 2.18, a single phase 3 kVA 240 120 volts 60 Hertz transformer has the following parameters: R HV, HV means high voltage side, 0.25 ohms, X HV 0.75 ohms, RLV 0.05 ohms, XLV 0.18 ohms. Just by looking to these parameters, you can observe that we do not have any information about the magnetized inductance. Okay, so the only model we can expect is the model that gives series impedance from the high voltage side to the low voltage side. We do not have any information here for the magnetized inductance. So you have two questions here, two sub-items A and B. Determine the voltage regulation when the transformer is supplying full load at 110 volts at 0.9 leading power factor. Leading, okay, that's important. You have to remember that a leading power factor would be because you have a capacitor. So if you have a capacitor, you expect your current to be leading. In addition, every time you have a leading power factor, a capacitor, you also expect your voltage to be a little higher because the capacitor will charge with the voltage and will maintain the voltage a little higher. Okay, so that's one of the effects of the leading power factor. Sub-item B, if the load terminals are short circuit by accident, determine the currents in the high voltage and the low voltage windings. So this would be like a short circuit operation by accident. Okay. So we have here on the same slide how we calculate the voltage regulation. The item A, voltage regulation will be V1 non-loaded minus V2 prime at loaded conditions rated divided by V2 prime rated loaded conditions 100% times 100, and V1 is related to V2 prime with the voltage drop across the series resistance and leakage reactance. So in order to understand this equation here, just go back to your model that we developed initially on this review. Okay, so go to the next slide. The equivalent circuit refer to the high voltage side, let's call it 1. So we take the variables refer to the low voltage side, let's call it 2. So I1 rated is 3000 divided by 240, that means 3000 VA, 3 kVA, divided by 240, the rated voltage. So that's the full load current. Your turns ratio is 240 divided by 120. So your rated value for I2 will be twice as that, 12.5 multiplied by 2, 25 amps. So here we can calculate the RLV prime as A square RLV, so is 2 square, 4, multiplied by 0.05, it's 0.2 ohms. The XLV prime is A square XLV, so is 4 multiplied by 0.18, 0.70 ohms. If you have your transformer at full load at 110 volts and 0.9 leading power factor, that means your V2 prime will be 220, 2 multiplied by 110. The phase shift is the inverse cosine of 0.9, is 25.8. So if you want to sketch your voltage and your current in time, you can sketch your voltage as a sine wave, could be a sine or a cosine. Okay, let's say it's a sine. So voltage is a sine. then your current will be starting before, because it's leading, before by 25.8 degrees. If you have 60 hertz, your period is 16.66 milliseconds. So that means 2 pi or 360 degrees. So you just make a proportion and you can easily sketch a voltage and current waveform. Okay, so that was a deviation, but just to emphasize a few important things. Coming back to this slide here. I2 prime can be calculated by I2 phase 25.8 divided by A. So it's 12.5 phase 25.8. Your V1 is calculated with the equation that we saw on the slide, on the problem statement. So you see here that we have 22 phase 0 plus 12.5 phase 25.8, okay, multiplied by the impedance 0.45 plus J 1.47, okay. So you have to know how to calculate phasors using complex numbers. When you have multiplication of complex numbers, you use magnitude and you add the phase, so that's a multiplication. When you have a division, you also divide the magnitude, and the phase shift is the phase of the numerator minus the phase of the denominator. If the denominator has a minus or if the numerator has a minus, you just consider that in your total phase. Is a phase of the numerator minus the phase on the denominator. When you want to sum complex numbers, it's easier to use Cartesian form. So Cartesian form for sum or subtraction, and use polar form for multiplication or division. Okay. So if you go to the next slide, the equivalent circuit as referred to the high voltage side is given here. So we have 0.25 in series with J 0.75. Then we have the referred variables from the low voltage side that we just calculated, 0.2 ohms and J 0.72 ohms. So V1 is your voltage on the right. V2 prime, no, V1 is your voltage on the left, V2 prime is your voltage on the right, I2 prime is the current that flows through the transformer. We are not considering here any magnetizing inductance that would be connected on the left, and you have to remember that there is an ideal transformer that connects the right terminals to take V2 prime into V2. So in order to calculate the voltage regulation, we have 217.9 minus 220 volts divided by 220 volts. You see here that your output voltage is a little higher because you have a capacitor. Okay. So your voltage regulation is minus 0.95%. So when you have a leading power factor, what happens to your voltage regulation becomes negative. When you have a lagging power factor, your voltage regulation is positive. Okay. So let's go now to the item B. Okay. When you short circuit the load terminals, you know that your impedance is 0.45 plus J 1.47. That comes from your previous model. So you can calculate your current in the high voltage winding is V1 divided by Z. Z is that. You can find the magnitude of Z, square root of the real part plus real part square plus imaginary part square. So this is 217.9 divided by 1.5373. The current in the high voltage winding is 141.74 amps. In order to find the current in the low voltage winding, we can multiply by 2, which is the turns ratio, okay? The inverse of the turns ratio, actually. So this is 2, because the turns ratio is a step down. This transformer step down from 240 to 120 volts, okay? But your current will be proportional to the inverse of the turns ratio, be multiplied by 2. The current in the low voltage winding is 283.48 amps. So I would like to suggest you some items for your own understanding. You can try several of those sub-problems here. You can draw the circuit for a PU single-phase model for the transformer that we just discussed, indicating all the required base. It's simple, and we have done this in our review. Then the second bullet, you can consider 3 of the same transformers used in a Y delta transformer, and you want to step down from a feeder, but that feeder is 2400 volts. Why I'm doing that? Well, first is an exercise, okay? Because in real life, you have to be sure that the voltage insulation will allow your transformer to be used for a higher voltage. But suppose you can, okay? Suppose you have a class of insulation that allows you to go up to 2400 volts, okay? So what you have now is a 3-phase transformer in Y delta. The 3-phase transformer is composed of 3 transformers. I want you to sketch such circuit, okay, the whole circuit, no model. With this, what's the maximum power you can have with this such 3-phase transformer? This is bullet number 3. Now, I want you to give me an equivalent per phase transformer model that represents this 3-phase connection. We discussed this in class. Please refer to my notes. There is a delta Y transformation. The square root of 3 comes into your effective turns ratio, okay? And you consider a per phase equivalent model, okay? A per phase equivalent model doesn't need to be in PU. It's per phase. That means I consider one phase to represent the total 3-phase transformer, because we are making the assumption that the system is symmetrical and balanced. Now the next bullet show a per unit per phase equivalent model indicating all the required base. So you take your equivalent per phase model and make it a PU model. Every time you have a PU model, you have to indicate the base. So you define the power base, the voltage base on the high voltage level and the low voltage side, the impedance base for the high voltage side and low voltage side. Then I want you to compare your original PU single phase model with this PU per phase equivalent model for the 3-phase transformer. So that's the bullet. Compare the per unit per phase equivalent model of the 3-phase transformer with the per unit single phase model for the original transformer, and discuss their relationship, because eventually you are using the same transformer for a 3-phase system, okay? So anything you know for the transformer should be useful for your final model in a 3-phase system. So I want you to discuss how they are related. So this is an extra problem with several bullets. It's just for your understanding. I'm not solving now. I really hope this review was useful. So just a reminder, your midterm exam this Friday is open book and open to your own notes, okay? So you should not use notes from somebody else, only your own notes. Your notes in your notebook, your notes in your tablet, your book printed, your book in your computer or in your tablet, but your stuff. And you have 15 minutes to finish. So you start right on time. I will be there 10 minutes before. I will give you the exams and we start exactly at noon. So have a good time, have a good learning, have a good exam, and see you on Friday. Thank you very much. Bye.